But the question is, what goes wrong? And you can feel hot without causing a pathology. So that's important, right? There are certain heat loads that you can tolerate and are well tolerated by both people and animals, but there is a threshold by which damage actually occurs. And the question then is, what is that cascade of injury? And for us, that's been a real interest in unraveling not only the order of things that go wrong, but also just the sheer scope of things that go wrong, and then thinking about the chronology of things that might go wrong. Some things go wrong early and then seem to be less important. Some things go wrong later and then seem to be of continued importance. And the other thing to remember is that it's a multi-systemic injury. And certainly the GI system gets a lot of attention because it's really obvious that animals don't eat so much.
Hello everyone and welcome to another episode of Swine Canada, brought to you by Wise Genetics. I'm Dr. Aline Remus, dedicated to bring you the latest insights and discussions in the swine industry. Get ready to expand your knowledge and stay ahead of today's episode. Today we're diving in a topic that is becoming increasingly critical: the biological impact of heat stress. And it's not just about being hot, it's about what is happening deep inside body when animals are exposed to persistent thermal stress. To guide us to the science, we're joined by Dr. Joshua Selsby, professor in the Department of Animal Science at Iowa State University. Dr. Selsby, thank you for joining me today. Welcome to the show.
It's a pleasure to be here. Thanks for having me.
For you at home, do not forget to like, follow, and share this episode with anyone that will be interested in animal health, heat stress and physiology, or resilient production systems. Dr. Selsby, how you decide to work in this field?
Yeah, so it was just a natural evolution of interests. When I started at Iowa State University some time ago, I wanted just to focus on skeletal muscle and skeletal muscle injury. And it just happened that I had colleagues that were interested in heat stress. And it was just such a cool, complicated, multi-systemic dysfunction that I was really, really interested in all the many things that were going wrong. And then it turned out that we didn't know a whole lot about what was happening inside skeletal muscle. And so it was a natural marriage of, interesting physiology and my own research interests. And then, boy, we've got our first little taste and we're up and running. And we've been going solid now for 15 years, working collaboratively with some great colleagues here at Iowa State.
Swine Veterinary Partners comprises 4 well-established clinics across Canada: Precision Veterinary Services, Premier SHP, Demeter, Ontario, and Demeter, Quebec.
I think you put it beautifully. I think you show the complexity of the area that you're working right there in that description. So if you can give our listener an overview of what heat stress is at the biological level, what is that is more than just feeling hot?
Yeah, so certainly you feel hot, but the question is, what goes wrong? And you can feel hot without causing a pathology. So that's important, right? There are certain heat loads that you can tolerate and are well tolerated by both people and animals, but there is a threshold by which damage actually occurs. And the question then is, what is that cascade of injury? And for us, that's been a real interest in unraveling not only the order of things that go wrong, but also just the sheer scope of things that go wrong, and then thinking about the chronology of things that might go wrong. Some things go wrong early and then seem to be less important. Some things go wrong later and then seem to be of continued importance. And the other thing to remember is that it's a multi-systemic injury. And certainly the GI system gets a lot of attention because it's really obvious that animals don't eat so much. Well, if they're not eating, they're not getting nutrients, and all of that is true. But what else is going wrong? And metabolically, what else is happening to these animals? Is it just as simple as they're not eating what they should be eating? Or are there other complexities that take place? And it certainly looks like there's a lot of other complexities that go well beyond simply the animal's not eating enough. If it was simply a matter of not eating enough, you can envision if you could somehow convince the animal to eat more, it would solve all the problems. And we know that doesn't work.
Yeah, and you just touched a very important thing there. You're talking about feed intake and how these animals are eating. There is some practical indicators that the producers can monitor to identify early signs of heat stress? Because when we get to the barn, one thing is when we feel hot and versus the comfort zone of a pig, right? Can you just walk us through these basics?
So there's certainly animals won't eat, and that's an early adaptation that takes place, an early change that takes place. But you might see other behavioral changes, like animals tend to sprawl out on floors if they're raised on concrete, looking for ways to cool. They certainly pant, and all of those things are pretty evident, and they happen pretty early in the heat stress response. One of the questions that we have is, what is the driver of the animals, to decrease feed intake? Is it rectal temperature, which takes time to actually increase, or might it be something as simple as skin temperature, which you'd envision could change very, very quickly if the animals are exposed to a heat? And we don't know the answer to that. It's like some of these initial triggering events are unclear.
And that's actually a very interesting question. And I think from the moment that you can actually pinpoint what that is, I think it's easier to take actions and understand the cascade of events that are happening there. But it's a very complex question and for sure answer. So just to tell us a little bit what persistent exposure to heat can cause to real physiological damage. What have you discovered about how the body, especially the skeletal muscle, responds to thermal stress?
Sure. In skeletal muscle, we see an initial dysfunction that appears to be pretty well regulated and cleaned up by just skeletal muscle being skeletal muscle and doing what it should do. So early on, say for the first 6 hours or so, there's an initial insult that's pretty well mitigated by internal mechanisms. And if heat stress were only, say, a 6-hour event, we really wouldn't be talking about it. But heat stress that tends to actually really continue much, much longer than that, that's when really it starts to get producers' attention. And what we see then is a resumption of damage inside skeletal muscle. So it looks as though there's an early inflammation that takes place, and that's quickly silenced by, say, 24 hours. And then there's a new set of injuries that occur. So there's a resumption of metabolic dysregulation. It looks as though the mitochondria are not functioning as well as they should, which is important for us because it's ultimately the efficiency of mitochondria can then be tied back to the efficiency of ATP production and the efficiency of growth. So how well are you using nutrients that are available to produce ATP? And if they're broken and they're not functioning very well, then it decreases production efficiency. The other thing is that when the mitochondria aren't working very well, it produces a lot of heat. So you have now inefficient mitochondria that aren't using the nutrients very well that are provided, and it's decreased nutrients that are provided, right? Because there's less nutrients that are coming in, and then they're not producing as much ATP, and as a byproduct, they produce additional heat. So it's a really a negative spiral that you end up with pretty quickly. So that's one aspect of what goes wrong. There are others, right? There's other cellular processes that we know aren't operating optimally. One of the ones that I get asked about a lot is this idea of protein degradation versus protein synthesis. So do the muscles shrink? And dogma has been that the muscles should be going through a degradation. And if you ask people, you'll hear things like, oh, the muscles break down. But as a muscle physiologist, I really want to know, what does that actually mean? So really, muscle breakdown, as you might say it, is a balance of synthesis and degradation. So how much protein are you building versus how much are you degrading? And right now, surprisingly, our most current data tell us that it's actually decreased synthesis, not an increased degradation. That's something we still need to validate, and there's other follow-up experiments that we need to do. But that's like the newest unpublished data that hopefully we'll be getting out sometime soon.
No, I hope to, because that's really interesting. I'm really looking forward to read that, because I think often when we're talking about the whole nutrient efficiency of utilization, we're always talking about synthesis and degradation, and we often tend to say exactly that. Well, it's just a higher turnover, but what that actually means, right? So that's so interesting. But like, just circling back, when you're talking about this effect that you have like 24 hours and then inflammation going back, it made me think of the it escaped me the correct term, cyclic stress. Made me think of cyclic stress. So there is a difference if you're in cyclic stress during the day, it's very hot, but during the night it cools down and the animals can go back and eat, or if they're constant in heat stress, and what is more common that you have been seeing in the barns?
That's a really good question. So for us, when we do things experimentally, a lot of times what we'll do is turn the heat on and leave it on, and so we don't allow the animals to cool. And in part, it's because we're interested in asking a biological question. So what is the effect of this chronic heat stress? But really, in practice, when animals are really heat stressed for days, yes, there is still some nighttime cooling, and there's a bit of recovery. But oftentimes, what happens during these heat waves that we really worry about in the industry, there's not adequate cooling that takes place in the nighttime. And so, is it cooler than during the day? Yes, but is it cool enough to provide relief to the animals? It's not. And so in that way, we simplify things from a model perspective and just use a constant heat stress. But we have done, and I should point out, we have done some cyclic heat stress experiments where we do modulate the temperature to more closely mimic, say, a 72-hour period with this unrelenting heat, with the understanding that even at nighttime, the temperatures still remain elevated, and it prevents the typical nighttime cooling that occurs. So to your question, this idea of inflammation. So systemically, we do see inflammation that seems to persist, and we see all sorts of changes in the distribution of immune cells across tissues. So leaving the blood, migrating into the blood, and that lasts throughout the heating experiments. Skeletal muscle is a little bit different. So in skeletal muscle, what we're seeing is an initial increase in inflammatory signaling. So skeletal muscle itself functioning and contributing to an inflammatory response. And that is activated, say, for the first 12 hours or so. But by 24 hours, that aspect and that role of skeletal muscle has been deactivated. And we don't know why, because all of the things that led to the initial activation of inflammatory signaling are still present. But something inside muscle essentially has turned off that particular pathway. And I have no idea what it is, but I think it's a cool thing to understand, particularly in the environment of heat stress, but also thinking about in skeletal muscle inflammation much more broadly, because it's certainly involved, inflammatory signaling is involved in a whole host of other states and other conditions in which skeletal muscle is a major contributor.
So that I get it right, I'm relating here to nutrition, and when we do depletion repletion studies, when we deplete the animal of a certain nutrient and then we give back, in some cases we'll see that in this response the animals will become much more plastic. Sometimes yes, sometimes no, but we'll see this response in terms of muscular level, where the tissue is trying to be more efficient. Is something like that you're saying that there is a change? And if there is this type of change, is it permanent or is just during the heat wave?
It's certainly not an increased efficiency. In fact, quite the contrary. So that you've really, with heat, the muscle is really damaged. And at this point, it's unclear if it's a direct effect of the heat, because muscle temperature does go up, or is it dependent on other factors that are in circulation that bathe the muscle? So we know, for example, the hormonal milieu changes tremendously from between a thermoneutral animal and a heat-stressed animal. And how does that impact skeletal muscle and skeletal muscle efficiency? I don't know. The other thing that I would say, though, is that during heat stress, it's the simultaneous, synchronous interaction of temperature, of changes in endocrine signals, of changes in circulating nutrients. There's pro-inflammatory cytokines that are zipping around. All of these things have an impact on skeletal muscle. And which one of those or which combinations of those are driving which effects, we don't know.
That's interesting. And that I'm particularly interested in understanding difference among individuals. I'm really working that individual variability. So I'm wondering if you saw difference between males and females, or even among individuals, of how they respond to heat stress.
Yeah, good question. Fantastic questions. So we do see differences with biological sex. And so right now we've limited our studies to just the production setting. So we're dealing with gilts and we're dealing with barrows. And within that setting, it appears as though gilts are more negatively impacted than barrows. And what that means in a reproduction setting, when you have, intact males, we don't know. And we also don't know the differences, of course, between barrows and boars. And all of these are questions we are really eager to address. And in fact, the United States USDA grants are due here in a month, and we'll be submitting some that aim to address some of those very questions. But you're also right in that, ignoring sex for a second, let's just focus on barrows, or let's just focus on gilts. There is variability around how severely impacted individual animals are, and I don't have a feel yet for what are the underlying causes, and certainly the geneticists, I think, could add a lot of value here in identifying certain genes or SNPs that are associated with resistance or susceptibility.
Just following up on that, do you think there is I would just I'll give you a little background, but when we study normal individuals and we try to understand difference in protein synthesis and variability, we see a lot of gene expressions that are related to oxidative stress that are showing up. And when you're telling me how there's all this difference, males and females and individuals, and I'm wondering, is there any link between heat stress, oxidative stress, and how male and females will respond, or individuals? Or I'm completely...
No, you're right on. Actually, it looks we're still trying to tease some of this stuff apart, but it looks like one of the big things is that the barrows, so the muscle from barrows, is somehow more able to adapt to the heat stress than is the muscle from gilts. And by that I mean, in gilts you see an oxidative stress, in barrows you don't. And in gilts, what you're seeing, there's a whole machinery dedicated to clearing out damaged mitochondria. And in gilts, that machinery is not activated, and in barrows it is. And so that we think is the basis for the difference between heat stress differences between barrows and gilts. This idea that for some reason, somehow, some way, that the muscle from barrows gets the same insult, or ostensibly gets the same insult, but is able to counter that insult with an effective response. Whereas in gilts, for some reason, it's not able to counter that stress.
That's extremely interesting. And what are some of the downstream consequences of heat stress that people might not expect, especially in terms of cellular health, metabolism, or even long-term resilience?
Yeah, that's also good questions, and also directions that we are hoping to move in. To your question about long-term consequences, we don't know. We did a study once where we heated animals for a few days and let them recover for a week, and we found, I think, at the end of heat there was a secondary immune response. And beyond that, we ended the study 7 days following our heat stress event, following recovery, and we should have gone longer. We just didn't know what we were going to find. And so at this point, we have no idea how long the effects of a heat stress last. So if you start thinking about this from a therapeutic perspective, let's say you could magically add some feed additive that would magically, eliminate the negative consequences of heat stress. The question is, how long do you have to give it? And do you preload it, or do you give it at the onset of heat? And then once the heat goes away and you achieve euthermia, do you stop or do you continue? And these questions are so unbelievably important when you think about this in an applied setting, but they have not been addressed. Really important questions. And the other thing that you asked about was some things that we didn't expect. Well, I had a grad student that started asking questions about the heart and wanted to know, what does heat do to the heart? And I don't know, let's go find out. And so we did, and it turns out the right ventricle and the left ventricle are differentially impacted by heat stress. And what's cool about this, it's from the same animal, so they're getting the exact same stress, or the exact same thermic stress. They're bathed in the same stuff, but the ventricles respond differently. So, and neither one is good, but they're bad differently. And you would expect then a different physiological consequence. And the reason this matters, you can start getting into animal welfare issues. You can start getting into replacement gilts. Are these things, do they linger or do they recover and there's no problems after that? But if you start looking then at deaths that occur in breeding herds, there are gilts that are sows at that point that are dying. because of heat. Deaths go up in the summertime. What's causing these deaths? And a lot of these are sudden deaths. Well, certainly if you damage the heart, that's a great way to have a sudden death. And so we're seeing things related to, it's called diastolic dysfunctions. The hearts aren't relaxing like they should between beats. And you end up with problems with calcium. And now all of a sudden the heart's we don't know, my guess is the hearts can't contract the way that they should be contracting. The other thing we're finding is that the kidneys are damaged. So not only then these critical organs, the heart, certainly need the heart to function, but if your kidneys don't work, you also don't survive. And so we tried this in a mouse model. So not exactly the same thing, but in a mouse model, the kidneys were just trashed. And we saw all sorts of, when you look at it under a microscope, there's all sorts of remodeling that takes place. And that's a fancy way to say they're damaged. Biochemically, they're damaged. And when you start looking then at blood variables to get some approximation of kidney function, you would see that they're actually decreased. And that is consistent with what we'd see in heat stress. So when you pull blood and you evaluate variables that are used to assess or approximate kidney function, they all point to the idea that kidney function has gone down.
You're saying heat stress. I'm wondering how hot has to be for the animals to be heat stressed? Because when you're telling me like this kidneys are damaged so badly, I'm just like imagining they're like 50 degrees Celsius,
No, so we don't bring them up too hot. Usually about 1.5 degrees to 2 degrees C. So what is that? About 3 degrees Fahrenheit. So it's not much. And certainly we're well below thresholds that would cause heat stroke, that would cause animals to lose consciousness. That's not our interest. That would be a really unusual event to take place in a production setting. But having these heat events, these heat stress events, that's fairly common.
Well, that is, it's not absurd. It's actually very normal and recurrent, especially if the warming temperatures is what we see on the regular basis. So it makes even more interesting and important. You're telling us you're really telling us, heat stress can have catastrophic effects in short and long term, because I imagine that a cell that passed by heat stress probably will have consequent problems. Have you seen anything? Do you see if like the heat stress will have consequences in the litter, and if these effects will follow, or have you done something like that?
A good question. So we did this work a number of years ago. This was work led by Lance Baumgart, who's been a longtime collaborator. And I apologize, I'll forget some of the outcomes, but they essentially did that. So they gave heat stress during various phases of gestation. And then they evaluated the offspring, and I think then some of the offspring were subjected also then to a secondary heat stress. My recollection is that just the animals that were subjected to heat stress in utero, depending on phase, I think there were differences in body composition, even though they themselves had never gotten a heat stress, as they were walking around. And then animals that were given a secondary heat stress after an in utero heat stress, I think they also behaved slightly differently than the ones that had been thermoneutral during gestation. So it appears as though there are some in utero effects that last, and we probably contribute a lot of that to epigenetic modifications that take place. But that's absolutely a thing. And I think, this is a place we can edit some things out. I don't know what I would like to add to that.
But with the rising temperatures, and we have more and more frequent heat waves, what are, in your findings, what is the most at risk population? Are we talking piglets, growing pigs, gilts? And how can we address? And what about the people working in the barns?
Oh, that's a good question.
It's like, if it happens with pigs, probably. Do you have seen anything in humans as well?
So these are fabulous questions. So not only are there more frequent heat events, but it also is apparent the duration of the heat events is increasing, as is the intensity. So all of these things are adding up to more heat stress. As far as the people go, working with pigs is actually pretty cool because it allows us to study an animal that is relevant for food production. Like that's the animal we actually care about. But it turns out the cardiovascular system of a pig is pretty close to that of a person. And so our expectation is that changes that are taking place in the pig are also taking place in people. So it allows us then to use this pig for a dual purpose. And that's a pretty unique thing. I mean, yes, we do work in mice, but to really represent what's happening in people, having a large animal model, just like a pig, is a really unique opportunity for us.
That is extremely important. And do you, my heading here to the end, do you see any practical solutions that you have seen that can minimize these effects, like nutritional or management?
So cooling is absolutely the best thing that you can do. If there are ways to keep the animals cool and prevent the heat stress from occurring at all, that is without question the best way to go. And then, of course, it begs the question, how do you do that? And obviously, if you could do that, I'd be out of business. So there's a bit of a caveat, and I've seen proposals where people are talking about using air conditioning in barns. I've even said the same thing, like that could be something that could be really reasonable. There are downsides, and if you're relying on solely on that kind of cooling, should there be an electrical grid strain or an outage, then you've lost your capacity for cooling, and that actually happens in the United States and elsewhere. Even in human settings, in communities where people lose functionality of the power grid. And there's also people that would point out, from an environmental impact perspective, that may not be the best way to go. So are there alternatives beyond that? I hope so. We've been wrong a number of times. We've attempted to protect mitochondria. That didn't work. Though I want to revisit it. I think we were right. We just missed it. We have attempted to increase the capacity for cells to clear out their damage, their damaged materials. That did not work. I think we may try some antioxidants and some targeted antioxidants. I have some hope that could work. And there's some other nutritional things that we might try. So one of the things that we're interested in now is how does pig metabolism change? And for a long time, we've been reliant on pulling blood, and then you measure, circulating fatty acids, circulating glucose. Is that really representative, though, of what's actually being used? And the problem with those measures is that it doesn't get to turnover. So all you get is a snapshot that says glucose is 100. But is it 100 because really nothing is coming in and nothing is coming out? Or is it 100 because lots and lots of glucose is flooding the blood and lots of glucose is flooding out of the blood? And I'm really interested in fatty acids. And there's good reason to believe that fatty acids really aren't mobilized to a large extent during heat stress, even though the animals aren't eating. But I think it's one of those things that needs to be explored and determined empirically that, in fact, fatty acid turnover doesn't go up. So again, we rely on our single measurements or snapshots of fatty acids, and it's, X. But is it X because there's really nothing in and nothing out, or is it X because lots comes in and lots comes out? And those are also grants that we're actually writing right now, just because we've reached a bit of a stumbling block, and we're looking at all of our data, and it's causing us to question assumptions. And it's causing us, not everything that we have here can be true. And so we're going back and we're asking, all right, if we made a mistake in our interpretation of all of this data, where is it most likely to have occurred? And then the other part of it is if something was misinterpreted, which would have the biggest immediate impact on pig production. And so for us, fatty acids are one of those things that we have an interest in.
That is very interesting. I'm looking forward to seeing good luck with those proposals.
It's time for our famous three.
Unfortunately, our time here is limited, so I'm going to have to head to our final questions. But for you at home, if you got questions or insights, please leave us your comment. Would love to hear your experience. And if you have questions about managing heat stress or more physiological insights, please leave some questions here to Dr. Selsby. Maybe he'll come back in another episode and answer them for us. We'll go for our famous three questions. So the first one is, what is your favorite science or heat stress related book or resource?
I'm cheating on this one. I realize that. I'm surrounded by world-class colleagues. And I was really thinking about this question, and it occurred to me as I was walking to one of my colleagues' offices. And I have access to world's experts in pig metabolism, production, applied sciences, genetics. I even have access to world's experts on the meat side. So yeah, I totally cheat. I rely on my colleagues more than I probably should, but I'm really fortunate to be in the environment that I'm in.
That is really fantastic. It also shows how teamwork has been very productive at IO. And what is your favorite book or resource outside agriculture or science?
Yes. So this is one I also put some time into, and it's not so much my favorite, but it impacted my thinking a lot. And there's a book called Freakonomics it's kind of an older book, but it looks at all sorts of data and thinks about them in different contexts. And I just thought it was such a creative way to think about data and to think about numbers and to identify relationships that it's one that I find myself thinking about and referring to often.
Very nice. And what you think sets a successful professional aside from those that are not?
Yeah, the best people that I've worked with in the industry and in academia, they all share these characteristics. All of them are creative. All of them have just an extraordinary work ethic. And then the last is all of them are patient. And so they're patient with themselves, they're patient with people, and it's those three characteristics I think really can make for a successful member of the community.
Very interesting. Thank you for that. And that's a wrap for today's episode of Swine Canada, presented to you by Wise Genetics. A big thank you to Dr. Joshua Selsby for helping us to understand the hidden toll of heat stress and the urgent needs to address it.
Thank you so much for having me. It was great.
And if you enjoyed this episode, be sure to subscribe, share it with your network, check out for more content at Wise Genetics. And once you're at it, let us know what topics you'd like to cover next and tag a colleague that you think should hear it. Thanks for tuning in, and this is Aline Remus signing off.